Stephen, the answer is no. No. So here we have the stresses. 0.85 F prime C are the stresses. But I need everybody's help here. Guys, if I give you the stress and I ask you to please find the maximum force, I give you the stress and I ask you to find the force associated with it, what would you do? Critical thinking. What would you do? You know, last Thursday, I started the presentation by giving you an equation that helped us find the stress. Given the force, how did we find the stress? The very first equation was an axial stress. Those of you who said sigma is equal to P over A, you are correct. Stress was load divided by the area. Now, let's think about that equation. If I give you the stress and ask you to please find the load that's associated with that, what would you do? You got it. Multiply by the area. All right? So Gary says you multiply by the cross-section. And Joseph O'Donnell also is giving me the correct answer. So here's what we are going to do. And I hope that you're still with me on this. 0.85 F prime C is the stress. So we're going to take that and multiply by the area over which it's acting. All right? So take that stress and multiply it by the area that it's acting on. Now, that area is equal to, what do you think? Well, that area is going to be equal to, this beam is like this. All right? And the cross-section that we're talking about, this stress is acting on, is like this shaded red. All right? Now, what is this dimension? Yeah, that dimension is equal to a lowercase a. All right? And what about the other dimension of that cross-section that this is acting on? You got it, b, which is the width of the beam. All right? So the bottom line is this. The area over which this stress acts is a, lowercase a times b. So there it is. The total compressive force is equal to 0.85 F prime C, that's the stress, times the area over which it's acting, which I just showed you what that area is. So that is A times B. Guys, this is the second or third step that you do, because that's always the same. So big C, capital C, is the total compressive force, and it's equal to 0.85 F prime C times A times B. All right? Now, this A, we really don't know what that is. We have to calculate the value of A. And it's called the depth of the stress block. The depth of the stress block. Now, one other thing that we need to identify before we move on, and that is the total force on the tension side. On the tension side, I explained to you, that would be where the steel is. All right? So, the stress that's acting on the steel is F sub Y. Fy, that's the yield stress of the steel that we're using. So we take that value, that will be given to you. You take that and you multiply by the area over which it's acting. Now here, the area that we consider is only the area of the steel, which is A sub S. So there it is. Let's go to all the way to the right-hand side of this page, and there it is. Total force, the total force in tension that we gain from the steel is simply equal to A sub S, the total area of the steel, times the yield stress of the steel. Now, I'm going to ask you something very fundamental. If we have, this goes back to statics. If we have two forces, that are equal, but they act opposite to each other, what is it called? Because that's one, the other one is here. So the total compressive force and the total tensile force, big C and big T, those, by the way, they have to be equal for equilibrium. So if they're equal and each one is acting in a different direction, what is that called? Kenneth says it's a couple. Caleb says couple. Lisa says couple. Donald says a couple. Yeah. So here we have a couple system. All right. Now tell me, what is the moment that's produced? A couple system, actually, a couple force system causes a moment. All right. Now, that moment, guys, that moment is called nominal moment. All right. So here's what I want you to understand. Remember, I told you you need to learn how to calculate the nominal moment acting on a concrete section. There it is. What we call nominal moment, guys, is nothing other than the moment that this couple system causes. And I just told you how you can identify the magnitude of those couple forces. All right? Now, the next thing I will ask you is, how do we, once we have a couple system, how do we calculate its corresponding moment, the moment they cause? Well, we just take one of the forces, because the forces are equal. You take one of them and the magnitude of one and multiply by the distance between the two. Multiply by the moment r. The distance between the two forces in this case is d minus a over 2. A over 2, that A is this thing, the depth of the stress block. D is important because I'm going to explain to you what D is. D is this distance. From the top to where the steel is. All right? That's very important. Now, this slide 18. Now, everything I said to you, we're going to put that in practice. We're going to do an actual problem, and you're going to help me with it. But this slide 18 basically goes through what I explained to you and also tells you the process, what we need to do in order to find the magnitude of that nominal moment. What I like to do is go through an example with you. All right? So tag this page 19 because I'll ask you to go back to it and take a look at it. But before we do an example, very quickly, do you remember, well, the fourth item on your list, when I said the following lists of items you need to learn, number 4 was what I called a beta 1 index. Beta 1, actually, if you don't mind, I'm going to go back to slide number 17, and let me see if I can get rid of some of these red lines. All right, well, I got rid of some of it. Okay, here's what I want you to take a look at, please. This A. Lowercase a is equal to beta 1 times C. All right? Now, C is this distance. This is the distance from the top to the centroid. But lowercase a is not the distance to the centroid. It is related to it, but it's not the distance. A is equal to beta 1 times C. All right? Now, I'm going to go forward. Here, slide number 20, it tells us what beta 1 is. And guys, sometimes they ask you this question, what is beta 1 for a given concrete. All right? So, and it's very simple. If you don't know it, you can sit there for the entire day and not know what they're talking about. But it's very simple. Beta 1 simply is a constant, and it's constant for a given compressive strength of concrete. So beta 1 prescribed by ACI code is equal to 0.85 as long as the compressive strength of the concrete is less than 4,000 psi. So the question would be the following. The compressive strength of a concrete is 3,000 psi. What is the beta 1 value for that? 3,000 psi certainly is less than 4,000, so there it is. Beta 1 is 0.85. If it is 4,000 psi, beta 1 is 0.85. However, for concretes that have a compressive strength higher than 4,000 psi, then you can use this equation to calculate the corresponding beta 1, or I just will explain to you in words. Beta 1 reduces 0.05, beta 1 reduces 0.05 for every 1,000 psi of increase. So pay attention. If beta 1 is 0.85 for 4,000 psi, so tell me, what is beta 1 for a 5,000 psi concrete? Well, that's 1,000 increase in compressive strength, so beta 1 will be reduced 0.05. So what would the answer be? 0.8. 0.80 if compressive strength is 5,000. Now, look at, this is very important, the very last line in the bottom of this page. It says beta 1 shall be greater or equal to 0.65. Well, when you read that, that is code talk. Those of you who are structural designers, you're probably familiar with that kind of language. But in simple words, what we're saying is beta 1, you can increase the compressive strength of concrete as much as you want, but there's a ceiling, there's a limit to how low beta 1 can go, and that is 0.65. All right. So anyway, for concrete of 5,000 psi, you reduce the beta 1 0.05, and it becomes 0.8 for a 5,000 psi. And what is it for a 6,000 psi? 475, correct. All right, very good. Let's move on. This goes back to that problem 2. Problem statement was given. You can go back. Helen, tell me, what slide number was it where we stated the problem? I think FY, the steel yield of steel, was 60,000. And here's what we need to do, actually. Step by step. Once you have the value, you have this sketch, we're going to calculate the value of T and value of C. These are the loads, all right? So T, the total load on the tension side, is AS times FY, this thing here. AS times FY. In this case, it comes out to be 180. This K, by the way, please just go ahead and write KEPS. That is 180 KEPS. Then we calculate C, capital C, the total compressive force. And I told you it's 0.85 F prime C times AB. Substitute. 0.85 is 0.85. This 3, it was given to be 3,000